So welcome everybody for this 7th installment of the Code of the Month organized by CASTIEL. We are very happy to have here Berg Hess from KTH in Sweden. He's professor at biophysics there, and his research turns around how to use molecule scale properties or interactions to derive effects on larger material scale. His tool of choice for that is GROMACS, and he's a long-term lead developer for GROMACS. And GROMACS is also one of the pilot codes of the lighthouse codes of the CoE, Center of Excellence BioExcel, to which Berg also contributes. So we are now eager to learn about GROMACS. Please, Berg.
Thank you. So thanks for the introduction and thanks for inviting me. I have some problems getting full screen sharing. I think I had the same problem last time, but I don't know what's the issue here. Maybe I should share my whole screen and then just go full screen. Sorry. Like this?
Yes.
Okay, good. Okay. Yes. Okay. So yeah, nice to be able to present GROMACS here. So I should note that I don't know what the background of the people attending is. So I'm usually used to give presentations for relatively targeted audience from life sciences or people already doing simulations. So this is a somewhat different presentation than I give normally. So I've tried to keep it very general at a high level. So I hope everyone can follow. If there are any questions, then you can ask. Obviously, and we have a lot of time at the end for questions. Okay, so this presentation is about GROMACS, which is a classical molecular dynamics code. So just a quick overview of the code. So it's an open source code, LGPL2 or later licensed. It is used for classical molecular dynamics simulations. And as a code, it's one of the most popular HPC codes worldwide. So we had, in 2023, we had about 10,000 citations, and it accounts for, according to one research company, for about 4% of the HPC used worldwide, so of all the HPC machines in the world. It's based on very efficient C++ code. It started out as one of the first major codes in C, but we moved to C++ a decade ago or so. It supports parallelization using OpenMP and MPI, as well as threads. Actually, I'll get to that later. And we have GPU acceleration targeting all major platforms using CUDA, OpenCL, and SYCL, and we're going to get HIP also. And development is supported by several EU projects, also some research grants, but one of the main funders is the BioExcel Center of Excellence. Okay, so then what kind of applications is GROMACS useful for? So it's in general, it's mostly used in the field of classical atomistic simulations. So one of the most popular fields of use is life sciences, biomolecular sciences, which is also the target of the BioExcel project. So I've shown here, for instance, a protein system. So typical, I mean, this is from our group, a protein and a membrane protein channel where one can look, for instance, at permeation of ions or so, or functionals, or also to see how one can develop new drugs or see how drugs function. Then we have an example of DNA. I mean, DNA, RNA, nucleic acids are a pretty popular field also. But then there's also more technological applications like polymers, for which I show here an atomistic view and also a coarse-grained view. I don't think in this particular case the coarse-grained simulations were done in GROMACS, but it is quite popular, especially with the Martini force field. And then on the right-hand side is a field which is becoming quite popular lately, is flow, where we're looking into, or I'm personally looking into, but also others, into how continuum dynamics appears from molecular systems, or to look at molecular scale effects in continuum flow setups. This targets larger scales often. Okay, so then what does GROMACS exist of? So GROMACS consists of several tools. So to be able to run a simulation, you need to prepare your system with coordinates, for instance, from the protein data bank, AlphaFold, or something self-generated, depending on where you get your input from. So there's a tool to generate a topology with parameters from a force field chosen by the user. There are also other tools available from other packages that generate topologies for GROMACS, so that can be converted. Then we have a pre-processing tool that generates a portable run input file that you can move to a HPC machine or wherever, so that contains all the information for the simulation. Then most effort goes into, of our development effort goes into developing the main MD Reynolds simulation engine, which is very efficient. So I'll discuss that in the next few slides. And then we have about 100 analysis tools. So this was one reason why GROMACS originally was quite popular, actually, because of the nice analysis tools. Nowadays there are also other packages, but we still have those around also to analyze mainly biomolecular properties, but also some other things. Okay, so then a general note, since I don't know what the audience, how much the audience knows about molecular dynamics simulations. So this is actually in many cases a general observation, but just to be clear about this. So the quality of a simulation is determined by, for one thing, the interaction parameters given. So that's the parameters in your model, which are given by the force field, which for atomistic systems consists of thousands of parameters. So these are very critical. So in GROMACS, we supply many different force fields, and there's also many force fields available one could download. Nearly all force fields have a GROMACS formatted version available. So this is not something we develop within GROMACS, because that's an effort, large effort by itself. So we just, people use the force fields developed by the community here. Then the second point for quality is accuracy of the force calculation in the integration. So this was an issue when I joined, or when I started in molecular simulation more than two decades ago. I think nowadays the field has this under control. So things are, well, you can of course do inaccurate things by making inconvenient choices, but most MD packages nowadays by default produce reliable results. So that's, well, there's a lot of effort that goes into this, but as a user, that's not something one usually has to worry about. And then the main issue nowadays, or together with the force field, is the sampling issue. So that's you need to sample sufficiently much of the conformations of interest of the phase space to be able to get reliable estimates for any scientific question you have. And that's proportional to the speed of the code. So the faster the code is, the more you can sample. So that's why in general molecular dynamics tools, and also on GROMACS, there's always the need for higher speed. So that's where a lot of effort goes into. So just a quick background. So we integrate Newton's equations of motion. So that's, the integration is really simple. So it's just, you need an integrator for that, but that's 3 or 4 lines of code. That's very easy. So what you need to compute, there's the force, which is minus the gradient of a potential. So that's where the cost of the simulation is, and that's where most of the optimization, the work in the code goes towards, is to computing these forces efficiently. So there's 2 main components which are the most expensive. There are many more other ones. There's the Lennard-Jones potential, which computes van der Waals forces in a repulsive and an attractive term. And there's the Coulomb interaction for electrostatics. And the Coulomb interaction is very long ranged, as you can see in this plot here. So I divided the Coulomb interaction for an oxygen atom in water by 100, and it's still pretty large. And especially if you often cut off the interactions at 1 nanometer or something around that. So for Lennard-Jones, that's okay. You see it's very small, but for Coulomb, it's not. So we need to do something better. So for that, we use long-range electrostatics. And the standard method in the field nowadays is particle mesh Ewald. So here you decompose the 1/r potential into a very quickly decaying part, the red part in the red dashed line in the plot on the right, and the complementary reciprocal space part, which is now very smooth. So we can compute this direct red part directly through computing pair interactions within a cutoff, and the long range we do using by spreading the charge on the grid, and then we can use the 3D FFT to solve the Poisson equation in reciprocal space, which becomes trivial there. It's just multiplication. So this is computationally very efficient in terms of flops, but it limits the parallelization. So because you need to transpose 3D grids in 2 directions to do the 3D FFT. So that's very inconvenient when running MPI parallelization, because you need to move a lot of data over the network. So recent development here, which I'll illustrate towards the end, is that we now have a hefty for GPUs to do parallel 3D FFTs on GPUs, so to improve parallelization. Okay, so then what kind of parallelization does GROMACS have? So we have a single node, we have OpenMP shared memory parallelization, yeah, OpenMP style. Then we also have another option, which is what we call thread MPI plus, oh, I forgot to correct the errors. It should be OpenMP, not OpenMPI there. So we have our own MPI kind of library, which is not actually MPI, but just uses threads, so that it's actually not using processes. But this allows us to optimize the number of ranks or threads for the performance. And it means that the user doesn't need to install an MPI version, which is convenient. And it also enables efficient GPU communication, because when there's not different processes, you can do some easy ways of communicating fast between GPUs. So then on multi-node, but actually also single node, we can also do the classical MPI plus OpenMP parallelization, where we have dynamic load balancing, where the figures on the right here show that one can resize all the domains independently. So we have a staggered grid to fully balance out the load. And then additionally, we have multiple program, multiple data parallelization, where we can do the 3D FFT and a few more things on separate ranks to reduce the number of ranks involved in a 3D FFT. This basically improves our scaling by a factor of 4. So this is a nice trick. So that's a high-level overview of the parallelization of GROMACS. Then on general MD performance, so often systems of interest have fixed size. So in particular, if it's biomolecular systems, you have your protein or your DNA or whatever that has a certain size, and then you need solvents. So you usually end up with something like 50,000 to 300,000 atoms. Nowadays, there are some bigger systems up to 1 million, which are coming within reach. So this means that we have a strong scaling problem. So there's no point in increasing your system size if you're interested in a certain molecule. So to get your answer faster or to get more sampling, you need to use more cores or more GPUs. So that means less work per core and shorter iteration times. So this is the challenge in molecular dynamics simulations, is that we have a strong scaling problem. So the time step is usually 2 femtoseconds. Sometimes you can double it to 4. So GROMACS can execute one time step in less than a millisecond. So you would need to, or you can in that way reach more than 100 million steps per day, or 200 nanoseconds per day. But you see that we need very many steps. So below here is a plot of the time scales we need. So we have a time steppage in the order of 10 to the minus 15 seconds. And then we have experiments on the order of, well, usually milliseconds, seconds or so, if you're lucky, microseconds. So you need to cover 9, 10 orders of magnitude there. So that's why there's such a high pressure for MD software to be very fast. And this also puts particular challenges on both the hardware and the software stack on HPC machines, because often hardware and software is not developed for such high iteration rates. For instance, we had issues with CUDA initially, that it was made for gaming, which at that point was 30 or 60 frames per second, but we run with iteration rates less than a millisecond. We run at more than 1,000 frames per second, so to say. And the overhead of any CUDA calls was much too high for us, so we were seriously hampered. Nowadays, that has been improved a decade ago or so, but this really puts a high stress on the hardware and the software stack. Okay, then some recent performance numbers. So this is on LUMI, which we put some effort into. So this is the largest supercomputer in Europe at the moment, and this is challenging because it has AMD GPUs, so there's no CUDA support, and there has been issues with the software stack, which is now kind of stabilized, so it can be used and tested. So our strategy for supporting LUMI was to use SYCL. So we invested in SYCL because that's an open source GPU programming model targeting Intel mainly, but on AMD for AMD there's an open SYCL project which converts SYCL to HIP code. So we actually compile HIP code in the end through OpenSYCL. And then we use, as I said, this hefty for parallel 3D FFTs over GPUs. So here's an example of a 1 million atom system scaling on 3 different machines, on Mahdi CPU, on Mahdi with a CPU plus GPU, NVIDIA A100s, and on Lumi G with AMD GPUs. And we see here the CPU version scales pretty nicely, nearly linear. The GPU version in general has a high overhead when going from 1 to 2 GPUs. So this is a known issue because of overhead. So we're working on reducing this. We already have some improvements here. But then you see from 2 to 4, the GPU scaling is very good. So this is and also from 4 to 8, where we really need the communication between the GPUs, the improvement is still there. So it's not perfect, but before having this parallel 3D FFTs, we couldn't do this. So this looks very promising, and these numbers will improve also as the code matures, and we both the GROMACS code and the FFT codes. So we're pretty hopeful. I was some years ago, I thought that scaling of MD simulations had stopped because of the GPUs getting faster, but the interconnects not. But nowadays the interconnects are getting a lot faster, so we can scale, as you can see here. Okay, so then some highlights of what GROMACS can do. So this is some particular things that we're put a lot of effort into, or we're proud of, or some things specific for GROMACS. So we have these are links from our website, or to our website. So we have a heterogeneous parallelization acceleration, where we try to use the CPU and GPU both to the largest extent possible. So we use both resources fully. By flexibly, we can move tasks forward and backward, also tune that. Then we have in the middle accelerated sampling. So this gets around the sampling issue to some extent by not waiting to cross barriers, but modifying the effective potential and crossing barriers faster. So this is a very powerful and flexible tool to accelerate sampling and to get free energies. Then we have a Python interface to a link to Python. We are planning to put a lot more work into this in the near future. Then there's QMMM, where we have a nice interface that interfaces with TCP2K, but it's easy to adapt that to any other QM code. So you can run QMM simulations. These are usually limited in performance by the QM code, not by the MM code, because QM is much more expensive. Then we extended this accelerated weight histogram to alchemical transformation, so you can do drug binding calculations or free energy of solvation in a very convenient and efficient way. And finally, there's the example of which is quite particular to the ion channel field, is to be able to apply fields in a consistent way by doubling the system and actually applying a charge difference over this. So one can look at the web page to see examples here. We have tutorials also for most of these things. Then a note on code development. So we have open development. We have issue tracking, code review, and CI/CD through GitLab, which has a diagram shown on the right. So we use the GitLab setup, but we have our own hardware running this to have support for all major architectures, particular GPU architectures. So any merge request that's pushed up goes through all our different hardware setups and our build setups. We have a yearly major release cadence, and we have roughly quarterly bug fix releases, and we have co-design efforts with all major vendors. So we have people working for GROMACS at both NVIDIA, Intel, and AMD. Some are internal here in the team, some are externally working. Right, that brings me to the last slide. So if you want more information, there's the website for general information, www.gromacs.org. There's the development, which happens at GitLab. So there's all the issues, the merge requests, and such are available there. There's tutorials available, official tutorials at tutorials.gromacs.org. There are many other tutorials from other groups in the world around as well. There's the forums to ask questions and discuss. There's a user discussion forum, a developer discussion forum, and an announce forum at gromacs.bioexcel.eu. And finally, I'd like to thank all the developers that contributed. So there have been many more developers over the years here. I just listed the people that contributed to the latest release. And thank you for listening. So now we should have time for questions.
Thanks a lot, Berg, for this very interesting presentation, which also gave insights into the algorithmic challenges of developing this type of code for large problems and on large systems. And the floor is open for questions.